Okay, here we go. Video number 2 for the week. Let me share the screen with you. All right, here we go. So this was your homework. I'm recording this all in one day. So when I say, were there any questions? Obviously, if there are questions, you've sent this to me, the email, and maybe we've done a Zoom meeting or something like that. But that's how we're going to work. I will always start with this slide. So maybe just to remind you, I didn't talk about it in the previous one, but you can do this at your leisure, but I need a copy of your homework as you do it. So easiest way, and if this isn't easy, let me know, is just take a picture of it with your phone and just attach it to an email. It's two things. It keeps you honest about actually doing your homework. It gives me a record that you've actually done your homework, and I can look it over and just see. So if as long as you're diligent about this and you're doing your homework, this is just one of those things that we have to do to make sure. You get really lazy by if there isn't a check step like this. I don't think you're a lazy person though. All right, so this is 8-1. We're going to do these 3 lessons for this week, and then call it a day. And remember, as the weeks progress, we're going to be meeting. We'll hammer this out at least twice a week for however much time it takes, just to discuss what we've done. And I will be asking you specific questions every week on the stuff we've done, just to make sure that you've got full understanding, and it gives you an opportunity to ask questions at that time as well too. So I intend to, every, let's say, Sunday, send out an email with the week's lessons, and it'll be all on YouTube stuff. So it'll be just the recording of me teaching the lesson that you can view at your leisure. In other words, if I'm taking too long, you've already got the concept, you can skip forward, that sort of thing. But I'm sure you're an expert at doing this stuff, watching videos type of thing. Okay, so we're gonna do 8.1 today. So that's a lot of homework. It seems like a lot. It's not as bad as it looks. They're very quickly done. All right. So obviously at this point you're pausing the video, writing this down. I'm going to continue onward. All right, this is a somewhat challenging lesson. There's going to be 2 distinct parts to it. The first part is fairly simple, but the second part is there's 3 patterns, and you really need to understand the patterns. So this is definitely one of those videos while you're doing your homework, you might want to replay parts of it and see how I did the particular problem until you get these patterns down pat. Nothing's changing for test wise. Same deal that applied in class when you were physically in class will right now mean that you can use a calculator at all times, and you can use your book of truth. So you don't have to memorize these 3 patterns, but you certainly need to do the 3 patterns. I will say this, of all the lessons in the book, this is the one where I think they do a really poor job of teaching it in the book. They don't really talk about the patterns. They really don't talk about there's really 3 formulas that come from the patterns, and they don't really present it as formulas, and I will. So I'm going to tap myself on the back and say, I think I do a better job than the book does on this particular lesson. All right. If I haven't already mentioned it, I love chapter 8. Love right triangles, and it's really fun part of geometry. I don't know if you know this or not, because I didn't have you for algebra 1, but whenever we have a proportion, 2 fractions set equal to each other, in the more formal parlance of math, we would say 2 ratios that are equal to each other, fancy words for 2 fractions that are equal to each other. We can do this thing called cross multiplication. I know you've done this before. You cross multiply, and you literally get to the same number. If I put variables in here, that means that A times D is the same as B times C. And if you had taken my Algebra 1 course last year, you have known that we can write ratios, fancy words for fractions, in different forms. And if you look there on the right of the screen there, this is called the colon form of ratios. The left side and the right side say exactly the same. And last year, you learned that those 2 things that are circled in red and blue actually have names. The ones in red are called the extremes. They're called the extremes because in ratio form, or I'm sorry, in a colon form, look there on the right, the A and the D are on the outside. So they're on the extremes of colon form of the proportion. And the middle part are called the means. All right, big fancy words. And if you remember, well, you don't remember because I didn't have your algebra 1, but for the students I had, I always say, remember, I said I would explain to you in geometry why they're called means and extremes, and then we will use those words to do something. Well, we've now arrived at that day. All right, what do you get from this slide? Cross multiplying works for proportions. All right, so that means that A times D is the same as B times C. If we put words in there, that would mean the product of the means is equal to the product of the extremes, or the product of the extremes is equal to the product of the means. Fancy words for A times D is equal to B times C. So if I take this proportion, I've just gotten rid of the other two letters, and now I've substituted X and Y for the means. So the means are now X and Y. The extremes are A and B. So the means are X and Y, and the extremes are A and B, and the product of the means is equal to the product of the extremes. So X times Y is the same as A times B, cross multiplication. Okay. So that's there in the box there in green. So what would happen if the means are equal? That doesn't mean the means are equal to the extremes. That means that X and Y are exactly the same value. That means X is equal to Y. Well, if X is equal to Y, it seems silly to use two different letters or variables to express the same value. So how about we just choose one of those letters for the means? What do I mean by that? I mean, pun intended, I mean that the means are literally just the letter X. That means on the ratio on the right, the mean is X, and on the ratio on the left, the mean is X as well too. So that means you've got the same value there. So if we did the cross multiplication now, well, let's see, the means is X, so X times X is X squared. So X squared will be equal to AB. And from the previous lesson, we know how to solve this. We take the square root of both sides. And so the square root of the squaring would cancel each other out. So you would just be left with X on the left side. So X would be equal to the square root of A times B. And this is what this is ultimately what we're doing today. The book tends to leave it in proportion form, the very top there. I like it in the bottom form there, because in the bottom is you're going to be solving for X today. And to solve for X, you're going to be taking the square root of the two numbers multiplied together. That's the cross multiplication. And so I prefer the bottom as our format, or as our formula to solve for the means. Now we make this way more complicated than it needs to be. We give this a name. We call X, where is X? X was the means of a proportion. We call X what's called the geometric mean. So it's a big fancy word for the square root of two numbers multiplied together that came from a proportion. So we call that a geometric mean. We better write some of this down. All right, so what is the geometric mean? It's the square root of two numbers that are multiplied together. So those are called the mean. There are two of these, by the way. One is called an arithmetic mean. You've done that one before. And now you just got introduced to the geometric mean. So the arithmetic mean, if you remember right, would be 2 or 3 or 4 numbers added together, and you divide it by how many numbers you have. Remember taking the average of something, you were taking what is called the arithmetic mean. So the arithmetic mean of 10 and 8, 10 plus 8 is 18, 18 divided by 2 is 9. That would be the arithmetic mean. Whereas the geometric mean would be take those two numbers, multiply them together, and then take the square root. Today, we're doing the right side. We're not doing the arithmetic mean. We're going to be doing the geometric mean. It's not a complicated thing. It's two numbers multiplied together, and then take the square root. All right, so arithmetic mean is the average of two numbers added. The geometric mean is the square root of the product of two numbers. So what just happened? We started off with a proportion where the means were exactly the same value. If that's the case, if you cross multiply, you get to this bottom equation where X is equal to the square root of A times B. The bottom is what we're going to be doing today. If you open up your book, they just concentrate on the top, the proportion, but in essence, we need to solve for X. Therefore, the bottom is the formula that we need. X is equal to the extremes multiplied together and take the square root. All right, we call X the geometric mean. So that's what just happened. Sounds really complicated, but it's not. So in your book of truth, let's write this down. And whenever I say this, I'm going to probably immediately start talking. Obviously, I mean you to pause the video and write this down. So an example of the geometric mean, they're going to give you two numbers and say, what is the geometric mean? Well, the geometric mean says take those two numbers, multiply them together, take the square root. So let's do that. 12 times 3 is 36, and the square root of 36 is 6. And is that all the geometric mean is? It sure is. Remember, if we were doing the arithmetic mean, that would be 12 plus 3 divided by 2. So 7.5. But the geometric mean is 6. Is it that easy? And the answer is yes. Geometric means are pretty simple. So now I will show you both the book approach and my approach of this. Obviously, I would rather you do my approach. You'll see why it's easier. Well, the book approach is they'll say, do the geometric mean of 3 and 10. So they want you to set up the proportion. There is the proportion for geometric means, where the means are exactly the same value. So x and x stay the same, but a and b become the 3 and the 10. And then you cross multiply. 3 times 10 is 30. X times x is x squared. And you solve this. Well, how do you solve this? I take the square root of both sides. So x is equal to the square root of 30. There's no perfect squares inside of 30. Now, that's all fine and dandy, and it's true. I would just say, if you remember that when you do the geometric mean, you multiply the two numbers together, and you take the square roots. So isn't that a little bit easier than setting up the proportion? I understand the book approach. They just want you to understand what's going on. But you do because you understand where geometric mean comes from. So I'm going to recommend you do on the right side. X is equal to the square root of 3 times the two numbers multiplied together. 3 times 10 is 30. There are no perfect squares inside of 30. Remember, we've got to maintain those 3 rules. No perfect squares underneath the square root symbol. No fractions allowed in your final answer. And if you have a fraction, you can't have a square root in the denominator. All right. One more time, geometric mean of 5 and 11. Let's see, doing it my method, you just multiply 5 times 11 and then take the square root. Are there any perfect squares inside of 55? No, 25 doesn't go into it. And there are no perfect squares. So that's the final answer. So this is why there's so many questions tonight for homework, because half of them are done this quickly. Half of them are done this quickly. So just take two numbers, multiply together, take the square root, and then remember we have to maintain the rules of the 3 customs or traditions of square roots. One more time, let's see. 9 times 4 is 36. Oh, that one's a nice one. The square root of 36 is 6. How about one of those weird ones, right? And this is the but one. All right. Geometric mean of 4 and 8. 4 times 8 is 32. Ooh, there's perfect squares inside of 32. So we give that a little bit of thought. Let's see, what goes into 32? I know 4 goes into 32 8 times, but so does 16. So I would recommend you, like I said, you give it the full 5 or 10 seconds of thought. Try to pick out the biggest perfect square that goes into 32. The square root of 16 is 4, so this is 4 root 2. Once again, I am absolutely positively going to talk fast in these videos. You can always stop and rewind and listen to it 2 or 3 times. All right, we good? All right, so that is half of the homework. Now I'm just going to still call this one easy, but it will take some time before it becomes easy. So the challenging part is understanding the patterns. I will prove these, but once you understand the patterns, it turns into an easy thing. There's going to be 3 of these. The math is easy. There's 3 patterns. The patterns are maybe complicated is not the right word, but there's 3 of them. So don't underestimate the challenge here. All right, so think about this. The process starts with a right triangle. The entire chapter is on right triangles. I'm going to take a right triangle. We know it's right there because C has got the little square there for 90 degrees. And I'm going to turn the triangle onto its hypotenuse. So the hypotenuse is sitting on the bottom. From angle C, I'm going to construct an altitude. Remember, the definition of an altitude is a line that goes through a vertice of a triangle and is perpendicular to the opposite side. That's the altitude. All right, so I made altitude CN. The other right angle there is because altitudes are perpendicular. That breaks this triangle up into 3 triangles. Which 3 triangles? Well, the one on the left, the one on the right, and the one that we started with. Using some different words to describe these, we could say the one on the left there is little, the one on the right there is medium, and the one that we started with is the large one. So we have the large one, we'll call it big. We have the one on the left, we'll call that one medium, and the one on the I said that left, I meant right. One on the right is medium, and the one on the left is the small one or the tiny one. So we get those 3 triangles. So I'm about to do a proof here, and what I'm going to prove is that those three triangles, the big, small, and medium, are all similar. All right, so how would I do this? So how would I prove that they're similar? Remember, we have those three magic bullets to prove that triangles are similar. We've got angle, we've got SSS, and we have SAS. And of those three, well, the easiest one and the one that you have to do the least amount of work with is AA. So we always like to reach for AA if we can. It's the easy. And by the way, if we look at this triangle, we have no side measurements. So there's no way we're going to get to SSS or SAS with this because we don't have any numbers to go with the sides. So yeah, I'm going to try to use AA. So let's see. I have three triangles, and I need to show that they're all similar. So I basically just pick two and show that those two are similar, and then pick another two, show they're similar, and pick the last two and show they're similar. So I'm going to start off by the first A, and that is that, well, of every triangle, the small, medium, the large one, there's one angle that's right. So there's the name of the right angles. There's ACB, CNB, and ANC, and they're all right angles. Therefore, they must be congruent because the definition of a right angle is that it's equal to 90. Okay, cool. So now I'm going to pick two of the triangles. I'm going to pick the big one and the medium one. That's the one on the outside and the one on the right. And if you notice, of those two triangles, the big one and the medium one, they share an angle. They share sides and angles. And the angle they share is angle B. They both are made up of angle B. Well, therefore, by the reflexive property, angle B is congruent to angle B, and there's my second A. So I just showed using angle that the big one, ABC, is the same as CBN. That's the one on the right there. That's the B medium one. So good, they're similar. We're going to do exactly that same trick for the big one and the small one. That's the outside one and the one on the left there. Same drill. Look, they both share angle A. So that means that there's your second A there. Angle A is congruent to angle A by the reflexive property. Therefore, the big one, ABC, is similar to the small one, ACN. And now if we look at those, if we look at the first, second, third, fourth statement there, and the sixth statement there, I have triangle CBN is similar to ABC, but ABC is similar to ACN. Therefore, by the transitive property, we have the final one, which is the small one, is similar to the medium one. Therefore, we are good to go. All three, QED, all three triangles are similar. That's a pretty cool, and it's a nice proof there. We don't get really much from it other than if this is the construction, if you start with a right triangle and make an altitude through the right angle to the hypotenuse of that big one, that you make three triangles, and the three triangles are similar. So this is our first theorem of the chapter. These are the three triangles. This is 8.1. I'm going to show you the whole thing. Pause the video because I'm going on. But this is 8.1. It says if an altitude is drawn to the hypotenuse, that means from C to the opposite side, then the two triangles that are formed, you made a left one and a right one, are similar to the original one. That's your third one. So in other words, all three triangles are similar. Now, pause right here, and then I'm going to continue. Okay, so we have theorem 8.1, which is a great and fine theorem. It's just that it's not very useful in and of itself. What is useful is two corollaries that we get from it. The but here is that we're going to get two corollaries. Remember, corollary are statements that come easily from a theorem. So both of these corollaries come from theorem 8.1. So here's the first one. And remember, I said the hard part of this section is there's three patterns. So this is going to be pattern number 1. So I'm going to compare the small triangle to the medium one. Let's see, that's ACN to CBN, ACN to CBN. So here's the pattern. If I take this blue side, which is AN, and the other side of the small triangle, CN. So those are not the hypotenuse; those are the short leg and the long leg of the small triangle. So that's blue and red. And I set that up as a ratio. So let's see, that would be AN over CN, right? There's my ratio. And I do the same, because remember, the sides of similar triangles are in a proportion. So if I do the same thing to the medium one, let's see, what was my ratio? Small leg to long leg. So I'm looking at the medium triangle, and I need the small leg or the short leg. Well, the short leg is CN. That's the red one. I'm looking at the triangle now on the right. Now I need the long leg, so I'm ignoring the hypotenuse. Well, the long leg is BN, right? We get that proportion. And I don't know if you see it, but if you look at that proportion, We got a geometric mean. Look, remember before we used x's? Well, now we have CN. I've got CN on the bottom of the left, and I got CN on the top of the right. So that gives us a geometric mean. And we know the form. And by the way, this is where the book stops. Well, I'm going to continue on to the actual formula. So if we do cross multiplication and take the square root, let's see, that would be Cn squared is equal to the square root of An, or equals to An times Bn, and then take the square root of both sides, that's geometric mean, we get to that. And that is what you need to write down. Yeah, there's words here, but in yellow there is the formula. So let's see, red is equal to the square root of blue times green. Red is equal to blue times green. So there's your first of 3 patterns. Yeah, there's words there. It says if an altitude is drawn to the hypotenuse of a right triangle, then the length of the altitude, that means the length of red, is the geometric mean between the segments of the hypotenuse. And that means the hypotenuse is made up of the blue and the green. Okay. So how do I remember this? The altitude is equal to the square root of the 2 parts of the big triangle of its hypotenuse. Notice AN and BN are parts of the hypotenuse of the big triangle. All right, so pause the video if you need to write all that down. Well, I should say pause the video and write all that down, but the yellow there is what you need to remember. One of 2 patterns. All right, this one starts with the altitude. So this one solves for the altitude of a right triangle. All right, so what just happened? We have this basic construction. If you have a right triangle and an altitude, that the red dotted line, which is the altitude, is equal to the square root of these 2 pieces, y and z. And y and z are parts of the hypotenuse of the larger right triangle. Pattern number 1. 2 more patterns. Very useful. Half your homework is on this. All right, it gets better because we get 2 more patterns. Now, if I were writing the book, I would have broken this up into corollary 2 and corollary 3 because you get 2 more patterns. Because the patterns are so similar to each other, they just write it as one corollary. Okay, so we're going to literally do the same drill. We're just going to get 2 patterns from this, but it's the same basic drill for each one. All right, so let's see what the pattern is. Oh, I'm going to compare big triangle to the small triangle. So I'm going to pick 2 sides of the big triangle. I'm going to pick the hypotenuse, and I'm going to pick the short leg. So I'm looking at the large triangle, ABC. So the hypotenuse is AB, and the short leg is AC. So that's my first ratio. And then I need I need some more. So let's see. Now I'm going to compare it to the small triangle. So let's see, I started with a hypotenuse. So the hypotenuse of the small triangle, that's the one on the left there, would be AC, and the short leg would be AN. And as you can see, once again, I just showing you the proportion, we got a geometric mean again. So the geometric mean for this one, big to small, would be AC is equal to the square root of AB times AN. I like the colors there. So if you think of the triangle, the big triangle there, the red is the short leg. So the short leg is equal to the square root of the hypotenuse times the small piece of the hypotenuse. In other words, the one on the left. And I probably shouldn't use a short piece of the hypotenuse because depending upon where the altitude is, it could be short or long. So let's see, red is equal to green times blue. Red is equal to the square root of green times blue. How about that? All right, so the second part of this, it does the same thing, same drill, except to the right side. I mean, it's the same basic pattern, right? Except that we're going to make a different proportion. So what do I mean by the same pattern, okay? So here's the basic pattern for the second one. For the second one, once again, it starts with the hypotenuse of the big one, and this time it goes to the long leg of the big one. And then I do the same pattern to the medium one. So the medium one, I start with the hypotenuse, that would be red. And if I go to the long leg, that would be this blue one. So we get another geometric mean, and there's the pattern. So once again, red is equal to green times, square root of green times blue. All right, so definitely take some time, write all of that down. In yellow, there is the pattern. Would it help to make this color-coded? Sure. Once you do a bunch of these patterns are quickly memorized and quickly forgotten. So you definitely need to have these in your book of truth. You'll do your homework, you do 2 of the same kind. You're like, ooh, I got the pattern memorized. And then this is just section 8.1. We're not going to see this again until the test. We're not going to actually even use this again until the test, so it's quickly forgotten. All right, so that's a Turkish stop sign. So we need to stop and do some practice here. So here's the three patterns once again. I'm going to show them to you really quickly. So the three patterns, one of them solves for the altitude. So red is going to be equal to green times blue. So what's the pattern? And square root of green times blue. So the pattern is the altitude is equal to the square root of the two parts of the hypotenuse of the big triangle. Second pattern solves for the left side. In other words, the short leg of the larger triangle. And let's see, that piece is equal to the square root of the hypotenuse times the same piece on the left side. Excuse me. So let's see, red is equal to, once again, square root of green times blue. And then the last pattern, we just do the same thing, but on the other side. So let's see, red is equal to the square root of the whole thing on the bottom times that same piece there on the right side. So it does have a nice, easily recognized pattern. But like I said, this is just section 8.1. There's 7 sections in the chapter. We're going to do something completely different for the rest of the chapter, and you're going to forget these patterns. So 100% make sure they're in your book of truth. All right, so let's throw some numbers and let's see how this works. These are just patterns. Once you just follow the patterns, the actual math is pretty simple. So this is what homework will look like. Let's see, it says calculate the unknown links. So if I look at the picture there, what's unknown is A, H, and B. A, H, and B. Okay. All right, so let's see. It doesn't really matter which one you start with. Corollary 1 refers to the altitude, so that would be the H. So let's see, what was the pattern? Let's see, red is equal to the square root of, let's see, the two pieces of the hypotenuse of a large triangle. So that would mean green times blue. So we got numbers there. So that means H is equal to the square root of, well, 3 times 7. Remember I said the math would be easy here. The hard thing is remember the patterns. 3 times 7 is 21. Are there any perfect squares in 21? Nope. So that's your answer. Done with H. Corollary 2 deals with the right side and the left side. It doesn't matter which one we start with. Let's start with A. So let's see. A is equal to the square root of the whole darn thing on the bottom. Well, the whole darn thing would be 10. And the same piece on that same side, in other words, 3, green times blue. And we're taking the square root. So see, the whole darn piece is not 3 or 7, it's 3 plus 7, which is 10. So 10 times 3, which is 30. And there's no perfect squares inside of 30. Once again, the math is easy. The patterns are a little bit challenging to remember. All right, the last thing would be B. It's same pattern except on that side. So it'd be the square root of the whole darn thing. That would be the green part times the blue part, which in this case would be 7. So let's see, 10 times 7, 70. No perfect squares inside of 70. So I can't really make this that challenging other than the patterns because the math is easy. Now, could they erase one of those numbers, 3, 7, and 10? They certainly can, and they will for homework. So if they erase the 7, well, they got to give you 3 and 10. Could they erase the 10? Sure, but 3 plus 7 is 10. So the only way they'll make it a bit more complicated is to erase one of those numbers, and then you just calculate that third number there by just using a little bit of subtraction or addition. All right, very powerful theorem. Allows you to solve for sides, right triangle without using Pythagorean theorem or something like that, or other techniques that we will learn. Certainly need to do another example. So this is really basically the same example, just the numbers have been changed and the triangle has been turned. So if you need to turn the book so it looks like that and matches what you have in your book of truth. Now, the only number that's missing here is the whole darn hypotenuse. Well, 7 plus 2 is 9. So even though they erased one of those numbers, it's there. But the process is still the same. Corollary 1 would solve for z, and corollary 2 would give you x and y. And it doesn't matter which one you do first. So corollary 1 deals with the altitude, which would be z. And the pattern for z is equal to the square root of the two pieces on the bottom, 2 and 7. So 2 times 7 is 14, no perfect squares. When are they going to give me some perfect squares? They will eventually. Corollary 2 deals with the other two sides, the x and the y. So let's see, x is equal to the square root of the whole darn thing on the bottom. That would be 9. 7 plus 2 is 9 times 2, the green times blue. They gave me a perfect square. The square root of 9 is 3, so that would be 3 root 2. Do you see what I did there? Okay, and the last piece, y, would be equal to the whole darn thing times that piece on the right there, so that would be 7. Let's see. 7 plus 2 is 9. We got another 9 there. Square root of 9 is 3. So we get 3 root 7. If you need to see that again, pause the video, rewind it, do that again. All right, one more. Look, hey, there's a number missing there. Well, that's pretty easy. They gave me the whole thing on the bottom, which is 100. 100 minus 36 is 64. So that piece that's missing there is 64. Okay, so let's see. X right there, the pattern was left side times the right side. The right side there is missing, but 100 minus 36 is 64. So it's 36 times, square root of 36 times 64. Now, look at what you got there before you do that multiplication. Hey, the square root of 36 is 6. The square root of 64 is 8. So yes, you can multiply 36 times 64, and then you gotta get find some perfect squares there. And it's much easier to do with smaller numbers than it is with bigger numbers. 6 times 4 is 48. Not too bad. How about this one? The pattern is x is this is corollary 2. The x is equal to the square root of the whole darn thing on the bottom, which isn't listed, but 36 plus 64 is 100 times 36. So 100 times 36. Where did I get the 100 from? 36 plus 64. That's the green portion. The square root of 100 is 10. Square root of 36 is 6. Will it always be that easy? No, but in this case it was. I gave you nice friendly numbers. So you get 60. All right, so I made the claim that the math was easy, the patterns were a bit more complicated. After you do a bunch of these, the patterns will be memorized. But once again, and I've said this before, this is only section 8.1, and we're not going to see this again until the test day. So one more. If this is challenging, flip the whole darn thing upside down if you want to, or maybe you can see this right from the start, but if you need to flip it upside down, you can. Let's see, what's the pattern? Let's see, the pattern we're solving for x, so the left side. So the left side is the whole darn thing, which, well, it's upside down. That's 16 times 12. So let's see. The pattern is green times blue, 16 times 12. The square root of 16 is 4. Oh, there's another perfect square inside of 12. Maybe that's too much to do in your head. So maybe take the 4 out first. 12 can be written as 4 times 3. The square root of 4 is 2. So you got a 4 times 2. Where did I get the first 4 from? The square root of 16 is 4. Where did I get the 2 from? Because 12 can be written as 4 times 3. The square root of 4 is 2. So we got a 4 times 2, which is 8 root 3. Okay. So we're combining the stuff that we did in the algebra review with some new stuff. Recall from last year, remember, we have those rules of perfect squares and non-perfect squares. Perfect squares are 25. Non-perfect squares, for instance, a square root of 10. And we always must look for the non-perfect squares if there are any perfect squares hidden there. There are no perfect squares hidden inside of 10, right? But there are perfect squares inside of 12, 4 times 3. So we yank out the perfect squares. Square root of 4 is 2, so we get 2 root 3. All right. I'll go ahead and let you do these on your own. Go ahead and pause the video and get these done. Let's see, what's the perfect square inside of 24? That would be 4 times 6. Square root of 4 is 2. What's the perfect square inside of 75? We've done this one a bunch of times. 25 times 3. So 5 root 3. 18, let's see, that would be 9 times 2. Square root of 9 is 3, so 3 root 2. And once again, many of these can be done without any work. However, it does pay off to write a little bit of work, and that way you're not doing too many steps in your head. All right, and okay, I know I call these the stupid or the dumb rules, but these are the rules. We can't have any fractions underneath the square root symbol. So we take the square root of the top and the square root of the bottom, so that would be 2/3. And the second one is that you can't have any square roots in the denominator. So even though we can take the square root of 4 and the square root of 3, the square root of 4 is 2, we wound up with the square root in the denominator. And remember, it's called rationalizing the denominator. We multiply technically by 1. We just write 1 as the square root of 3 over the square root of 3, which would give you in the top, multiply straight across, 2 root 3 over the square root of 9. Square root of 9 is 3. So you get that. And like I said, the argument is that doesn't look any more simpler than what we started with. But remember, the power is that if we ever had to add, subtract, multiply, and divide, it would make it easier. All right, so we got 3 left, and that'll be it for this lesson. All right, so let's see what we can do here. So square root of 18 would be 9 times 2. Square root of 9 is 3, and 3 times 5 is 15. Second one, let's see, I can't take the square root of either one of those. So it's the square root of 3 over the square root of 2, but we're not allowed to have the square roots in the denominator. So we multiply top and bottom by square root of 2. Square root of 3 times square root of 2 is 6. 2 times 2 is 4. Square root of 4 is 2. Last one, so you can't have a square root in the denominator, so we multiply top and bottom by the square root of 5. Multiply straight across. 15 times square root of 5 is 15 root 5. In the bottom, we get the square root of 25, which is 5. And look, we can do some reducing there. 5 goes into 15 3 times. And there you go. All right, if there are any questions, send me an email. If not, we are done with today's lesson.